You know, everything around us is moving, literally everything. But have you ever stopped to think about how we actually describe that motion? I mean, with the kind of crazy precision you'd need to, say, land a rover on Mars or design a mind-bending roller coaster? Well, it turns out there's a powerful mathematical language for that, and today we're going to learn how to speak it. So let's just jump right in with the big question. How in the world do we mathematically pin down an object's path through space? It sounds simple, right? But think about it. Something can twist, turn, speed up, slow down, all in 3 dimensions. We need some kind of tool that can wrap its head around all of that at the same time. Okay, take a look at this. Imagine you're this hang glider, catching a thermal and just spiraling up, up, up. That path, it's not just a simple up and down or left and right, is it? No way. It's this beautiful, complex dance in 3-dimensional space. So the real challenge is, how do we capture that whole journey in a single, elegant piece of math? That's what we're here to figure out. Well, the answer, as you might have guessed, is a special kind of mathematical language. One that's literally built from the ground up to describe motion. And that's what we're going to do right now. We're going to unpack its grammar piece by piece so you can see for yourself how it perfectly captures that incredible dance of objects in space. All right, let's get into the good stuff. The core tool, the absolute foundation of all this is something called a vector-valued function. Now, the best way to think about it, it's like a cosmic GPS. Seriously, it's a system that can give us an object's exact pinpoint coordinates at any single moment in time. So how does this cosmic GPS actually work? Well, it's pretty clever. You give the function a really simple input. Let's just call it t for time. And in return, it gives you a single output, a vector. But this isn't just some random arrow, no. This vector is like a pointer. It reaches out from the very center of your coordinate system and points directly to where the object is, giving you its x, y, and z coordinates all in one shot. So for every single tick of the clock, you get a new pointer, and together they trace out the entire journey. Okay, before we get too crazy, let's bring this down to 2 dimensions. You've probably seen something like this before. It's often called a parametric curve. It's super simple. As our time variable, t, just ticks along, the function, we'll call it r of t, draws out a path on a flat piece of paper, basically. It's a fantastic way to visualize how the x and y positions are changing together over time. But this is where it gets really cool. All we have to do is add one more piece, a third component for the z-axis, and suddenly, boom, we break free from that flat plane. Now we can describe any path in 3D space. Remember that amazing spiral from the hang glider? We can map that now. We're not just doodling on paper anymore. We are literally mapping motion in the real world. Okay, so we've got the where figured out. We can pinpoint an object's location. But honestly, that's only half the story. The really interesting stuff is understanding how it's moving. And to unlock that secret, we've got to bring in the big guns, calculus. So just to recap real quick. That vector function, r of t, that's our position. It's the where. It tells us the location at any given time t. But what happens if we take the derivative of that position function? This, my friends, is where the magic really happens. See, a derivative is all about one thing, the rate of change. So when we take the derivative of position, what we're really asking is, okay, how fast and in what direction is the position changing right now? And the answer to that question? That's velocity. So that first derivative gives us the velocity vector, v of t. And I want to be super clear here. This is way more than just a number for speed. It's a vector, which means it tells us 2 absolutely crucial things at once. Which direction the object is heading, and this is key, its length tells us the object's speed. And we're not going to stop there. What if we take the derivative again? Well, now we get the acceleration vector a of t. And what does that tell us? It tells us how the velocity is changing. Is the object speeding up? Is it slowing down? Is it making a turn? Acceleration has all the answers. And this is where we really start to see the connection to physics, because acceleration, that's the direct result of forces. And check this out, because it's such a brilliant visual. The velocity vector, at any point on the path, is always tangent to the curve. It literally points exactly where the object is going at that one precise instant. The perfect analogy is the headlights of a car on a winding road at night. They're always pointing straight ahead, right along the curve of the road. All right, we've talked a lot about the dynamics, the how and why of the motion. Let's switch gears for a second and talk about the path itself. We know the route it took, but how long was that route? How far did the object actually travel? The concept for this is called arc length. And honestly, the best way to think about it is as the odometer for the journey. That's it. Imagine you could just grab the ends of that curvy path and stretch it out into a perfectly straight line. The length of that line, that's the arc length. It's the total distance you traveled, plain and simple. Okay, so we know how long the path is, but what about its shape? I mean, how can we put a number on how sharply a path is bending at any given spot? Think about it. A straight road is super easy, right? It doesn't bend at all. But what about a crazy hairpin turn on a mountain road versus a long, gentle, sweeping curve on the highway? There's a difference. So how can we actually assign a number to measure that sharpness? The answer is a concept called curvature, and we use the Greek letter kappa for it. Just think of it as a number that tells you how tightly the path is turning. A gentle curve? Low curvature. That insane hairpin turn? Very, very high curvature. And a perfectly straight line that doesn't bend at all? You guessed it, its curvature is 0. It's our go-to mathematical tool for measuring bendiness. All right, we're in the home stretch now. For this last part, let's tie all of these math ideas back to where we started, the real physical world of forces. Now this is the really crucial point. The motion we've been describing doesn't just happen randomly. It's not magic. It's caused by real-world forces, things like gravity, tension, friction, you name it. And the amazing part is, the grand total, the net result of all those pushes and pulls, is captured perfectly by that one thing we already figured out, the acceleration vector. But get this, we can break acceleration down even further into two distinct parts that each have a very specific job. First, there's the tangential component. Think of this as your gas pedal and your brake. It only acts along the path to change your speed. Then you have the normal component. This one points inward, toward the center of the curve. This is your steering wheel. Its only job is to change your direction. And what's so incredible is that these ideas are totally universal. The exact same math we use to break down the acceleration of a race car screaming around a track is the same math that describes the force of gravity keeping our planet locked in orbit around the sun. It is the one language for motion on every single scale. So there you have it, a complete language for talking about and analyzing motion. We started with just a simple position vector, and from that one idea, we got velocity, we got acceleration, and we even figured out the shape of the path itself. It's incredibly powerful. And it leaves us with a really big question. Now that we have this tool, what else in our world can be modeled with the language of vectors? What other incredibly complex systems, from the flow of ocean currents to maybe even the wild swings of the stock market? What else can we understand better just by looking at it through the lens of vectors?
Have you ever seen one of those buildings that just stops you in your tracks? And you think, how in the world did they build that? Well, that's a great question. But I think there's an even cooler one. How did they even calculate it? And that's what we're going to get into today, because it turns out some of the most jaw-dropping designs out there are really just beautiful math.
Okay, just look at this thing. Seriously. This is the hemispheric building in Valencia, Spain. It's designed to look like a giant eye. They call it the Eye of Wisdom. And it even looks like it blinks with this huge gate that moves. I mean, it's absolutely stunning, right? But for us, it's also a fantastic math problem.
So, let me ask you, how would you even start to figure out the volume of a shape like that? I mean, it's not a cube, it's not a sphere, so what formula do you use? How do you measure the space inside all those crazy flowing curves? Well, stick with me, because that's exactly what we're going to figure out.
All right, Section 1, an architectural puzzle. Let's really dig into what makes this building such a tricky problem to solve. So, get this. Inside that giant eye is an IMAX cinema, a massive one too. But here's the catch. The very thing that makes it beautiful, all those complex curves, is also what makes it a total headache to measure. You can't just use your standard high school geometry formulas here. It's just not going to work. We need something more powerful.
So, that brings us to Section 2, beyond basic geometry. Yeah, we're going to have to leave the easy stuff behind for this one.
Okay, so this really lays it out. On one side, you've got your standard shapes, right? Cubes, spheres, cones, the stuff we all know. They've got simple, easy formulas. But then you look at the hemispheric. It's all these complex, organic curves mashed together. There's no single plug-and-play formula for that. We definitely need a better tool.
And I love this quote because it perfectly sums up what we're about to do. The essence of mathematics is not to make simple things complicated, but to make complicated things simple. That's the key. We're not looking for a more complex way to do this. We're looking for a genius mathematical trick that makes this complicated thing simple.
And that brings us to section 3, building with infinite slices. And trust me, this concept is as cool as it sounds. It's an amazing way to wrap your head around a really big idea in math.
Now, the official fancy name for this is multiple integration. I know, sounds scary, but don't tune out. The idea behind it is actually super simple. It's like this. If you have a giant, weirdly shaped object you can't measure, what do? Well, you just break it down into a ton of tiny, simple pieces that you can measure, and then you just add them all back up. That's it.
So think about it like this. Step 1, you take our complex building. Step 2, you imagine slicing it up into an insane number of microscopic little cubes. Think of them like cosmic Lego blocks. Now, step 3 is easy, right? Finding the volume of one tiny cube is simple. Length times width times height. And finally, step 4, you just add up the volumes of all those billions and billions of tiny cubes.
And believe it or not, that's the core idea. This whole slicing and summing thing, that's the heart of integration, a huge part of calculus. You're basically using an infinite number of super easy calculations to solve one single, ridiculously hard problem. It's genius, really. All right, section 4, modeling a modern marvel. We've got our secret weapon. Now let's go back and actually use it on that building. So obviously, you can't just shove a building into a math equation. It doesn't work like that. The first thing mathematicians do is create a model. We're going to approximate the building's super complex shape by using two much simpler shapes that we do know how to work with, one tucked inside the other.
And here's what we're going to use. For the outer shell, that big, beautiful eye shape, we can model it as an ellipsoid. Just picture a sphere that's been stretched out a bit. It's a near-perfect fit. And for the cinema inside the pupil of the eye, well, that's easy. We can just model that as a perfect sphere.
Okay, first up, the outer ellipsoid. Now, when you apply that whole slicing and summing idea in 3 dimensions, which, by the way, is called a triple integral, you actually end up with this really nice, clean formula. Volume equals 4/3 pi times a, b, and c. And don't worry, a, b, and c are just the distances from the center to the edge in each of the 3 dimensions. Simple as that.
So you take the real-world measurements from the lemmaspheric, plug them into that formula, and you get 392,699 cubic meters. Boom! Part 1 of the puzzle is solved.
All right, now for the inner sphere, the cinema. This is a formula a lot of us probably remember from school. Volume is 4/3 pi r cubed. But here's the cool part you might not have known. This classic formula, it also comes from that same slicing and summing method of integration. It's all connected. We plug in the numbers for that inner sphere, and we get a volume of 33,510 cubic meters. Okay, now we have both our numbers. We're almost there. So we've got the volume of the whole thing, and we've got the volume of the bit in the middle. How do we find the volume of the space between them? Well, after all that calculus, the final step is the easiest part. It's just simple subtraction. You take the big number, subtract the small number, and there it is, our final answer, 359,189 cubic meters. And that is the volume of that incredible, beautiful space that at the beginning seemed pretty much impossible to measure.
Okay, section 5, the world, integrated. Because this whole idea, this slicing and summing thing, it's not just for cool architecture. This is one of those concepts that's secretly running the world all around us.
Here's a totally different example. Ever wonder how weather forecasters figure out how much rain fell over, like, an entire state? They use the exact same method. They basically lay a grid over the map, measure the rainfall in each tiny little square, and then, you guessed it, they add it all up. That's integration right there, helping predict the weather.
So when you boil it all down, this one powerful idea, taking something complicated and breaking it into a million simple pieces, it lets us measure just about anything, from the grandeur of a building to the chaos of a storm. It really is like a hidden language that our world is written in. And that leaves me with one last thought for you. Just look around you right now, at the clouds outside, a mountain in the distance, or even just the weird shape of the coffee mug on your desk. After all this, what's a complex shape in your world that you now realize you could actually measure?
Okay, let's just jump right in. If you want to describe pretty much anything that moves or pushes or points in the world around us, I'm talking everything from a planet zipping through space to the wind on your face, you need to speak a certain language. And that language, well, it's built on one single idea, the vector. Today we're going to unpack how these things let us describe, calculate, and literally build inside our 3D world.
Think about it like this. A pilot knows where they want to go and how fast. But what happens when the wind kicks in? You can't just add the speeds together, right? You got to count for the wind speed and the direction it's blowing from. See? You're already thinking in vectors. We're just going to give that gut feeling some real mathematical teeth.
So here's the game plan. We'll start with what a vector even is, then we're going to grab our two most important tools, the dot and the cross products. Once we've got those, we'll see how to literally draw lines and build entire planes in 3D space, and then we'll see how all this stuff pops up in the real world.
All right, first things first. What exactly makes a vector so much more powerful than a plain old number?
This is the absolute heart of it. A regular number, what a mathematician would call a scalar, just tells you how much. Like it's 72 degrees outside. A vector, though, tells you how much and which way. So it's not just a speed of 50 miles per hour, it's 50 miles per hour heading north. That combo of length and direction is its superpower.
So let's hop back to our airplane. The engine is pushing the plane forward with a certain speed and heading. That's one vector. The wind is blowing with its own speed and heading. That's another vector. You add them together, tip to tail, and boom, you get a new vector that shows where the plane is actually going and how fast it's covering ground. That's vector addition, right there.
And it's the exact same idea on the water. A boat's engine gives it one vector, but the river has its own current, its own vector. To figure out where that boat's going to end up, you have to combine them. It's the same math, just a different setting. Pretty cool, huh? And hey, vectors aren't just for things that are moving around. Here, gravity is pulling that weight straight down. That's a vector. But the tension in those two cables, they're pulling up and out, each one its own force vector. For that weight to just hang there perfectly still, all those vectors have to be in a perfect tug-of-war, balancing each other out completely. Okay, so adding vectors is one thing, but to really start doing cool stuff, we need two key operations in our toolkit, the dot product and the cross product. Now they sound kind of similar, but they answer totally completely different questions.
And this slide just lays it out perfectly. On the left, you've got the dot product. You put two vectors in, and it spits out a single number, a scalar. Think of it as a tool that measures how much two vectors are on the same page. On the right, the cross product. You put two vectors in, and you get a brand new vector out of it, pointing in a totally new direction. It's all about finding orientation. Let's dig into that dot product for a second. Its value is tied directly to the angle between the two vectors. So if two vectors are pointing in the exact same direction, their dot product is as big as it can be. But if they're perpendicular, at a 90-degree angle to each other, their dot product is zero. They have nothing in common.
So the way to think about it is this. The dot product is like asking the question, hey, how much of this first vector is really going in the same direction as the second one? It's like it casts a shadow of one vector onto the other to measure the overlap. And here is a perfect real-world example from physics. When you pull this wagon, you're pulling kind of up and forward, right? But it's only the forward part of that pull that actually makes the wagon move. The dot product lets you find exactly that useful part of the force, the component that's aligned with the motion to figure out how much work you're actually doing. Okay, now for the cross product. This one's special. Its superpower is creating a third dimension out of two. You take two vectors that are sitting on a flat surface, do the cross product, and you get a new vector that points straight up, perfectly perpendicular to that surface. This is the absolute key to figuring out which way things are facing in 3D. So now that we have our toolkit, we can go from just talking about forces to actually building stuff. Let's start with something simple, a straight line floating in 3D space. It sounds way more complicated than it is. To define an entire, infinite line in 3 dimensions, you only need two little pieces of information. First, you need a starting point, any single point that the line passes through. And second, you need a direction vector to tell you which way to go. And you can see exactly how it works here. You start at your point P. From there, you can get to any other point on that line just by traveling along your direction vector, V. Travel forward a little bit, you're at a new point. Travel backward a whole lot, you're at another point. It's like a recipe for the entire line.
All right, we've drawn a one-dimensional line. What's next? Well, let's build on that and define a two-dimensional plane. You know, like a flat sheet of paper or the surface of a wall, but floating anywhere in space.
And guess what? It's just as simple. Just like a line, you need one point to pin it down in space. But instead of a vector that points along the surface, you need what's called a normal vector, one that tells you which way the plane is tilted. And how do you find a vector that's perfectly perpendicular to a surface? Yep, the cross product.
This picture shows it perfectly. That gray grid is our plane, and that orange vector sticking straight out of it, that's the normal vector. It basically defines the up direction for that specific surface. Every point on that whole infinite plane has the same relationship to that one normal vector, which is how we can describe the whole thing with just one clean equation. I know this can feel a little abstract, but I promise you these ideas, from adding vectors to finding these normal vectors, are the invisible engines running behind so much of our modern technology. Take a look at these radio telescopes. When they look at a star, the signal hits each dish at a slightly different time. Well, using vector math, astronomers can perfectly combine all those signals, correcting for those tiny time differences, and essentially turn dozens of small telescopes into one single, massive virtual telescope. It's amazing. And if you've ever played a video game or seen a CGI movie, you've seen this in action. How does a game engine know how light should bounce off a car or a wall? It's all vectors. The program finds the surface's normal vector, the same one we just talked about, and uses dot products and other vector math to figure out exactly how light should reflect to create those realistic shadows and glints.
And it's not just in the virtual world. These incredible sweeping curves you see in modern buildings are literally born from vector math. Architects use computer-aided design software to map out these complex surfaces using the vector equations for lines, planes, and curves, letting them build structures that would have been totally impossible just a generation ago.
So from the stars, to video games, to the buildings we live in, vectors are the language we use to describe our 3D world. They're the fundamental building blocks. And the cool thing is, once you start to understand this language, you really do start to see it everywhere. So the only question is, what will you use it to describe?
So, you want to multiply vectors? Well, today we're breaking down the two main ways, dot and cross products.
See, with vectors, it's not as simple as just multiplying numbers. There are a couple of ways to do it.
Yep, we've got two big ones, the dot product and the cross product, and they are totally different.
First up, the dot product. You multiply two vectors, and what do you get? Just a single number, a scalar.
But the cross product? That's a whole other story. It actually gives you a brand new vector.
So that's the key difference. Dot product gives a number. Cross product gives a whole new vector.
Okay, so what do these things actually mean? Let's look at the geometry behind them. The dot product is all about alignment. Think of it as how much one vector agrees with the other.
Yeah, it's basically the projection of one vector onto another, kind of like its shadow. Now, the cross product's magnitude, that's the area of the parallelogram these two vectors create.
And the new vector it creates? It's always pointing straight out, perpendicular to the first two.
So when would you actually use these? Let's get into some real-world examples.
Okay, picture this. You're pulling a wagon. The dot product helps figure out the useful part of your force.
Because work only cares about force in the direction you're moving. That's pure dot product.
All right, now for the cross product. Its classic use case, torque. You know, a twisting force.
Torque is all about rotation, which needs a new direction. An axis. That's a job for the cross product.
So let's nail this down. Dot product is for alignment, like work. Cross product is for area and torque.
So the next time you have two vectors, just ask, do I need a number or a whole new direction?
Let's unpack one of the coolest visual ideas in all of multivariable calculus.
To really get this, let's just imagine we're a hiker on this mountain.
So you're standing there and you gotta ask, which way is the steepest path up?
Trying to figure that out in 3D is tough. What you really need is a map.
And that tool is a topographical map, which basically flattens the mountain onto paper.
Now you see these lines, each one connects points that are at the exact same height.
In math, we call these level curves. They're basically paths where you don't climb at all.
Here's the key though, how steep it is totally depends on which direction you walk.
So let's compare two choices. You could take path A, or you could take path B. If you walk along a level curve, it's an easy stroll. Your elevation doesn't change.
But if you cut straight across them, whoa, that's a serious climb, super steep.
This idea of slope in a certain direction, that's called the directional derivative.
But how do we find the one direction that's the absolute steepest way to the top?
For that, imagine you have a magical compass. And no, it's not pointing north. Instead, it always points you in the direction of the steepest climb from right where you are.
And this magical compass has a name in calculus. We call it the gradient vector. Okay, so let's put it all together. Level curve, meet the gradient. Here's the reveal.
It's simple logic, right? The direction of zero change must be perpendicular to maximum change.
Think about it like this. The fastest way to cross a road is to go straight across.
That's why the angle between that easy path and the steepest path is always 90 degrees. So your gradient is the perfect calculus compass, always pointing you up that steepest hill.
And this is huge because it helps us find the fastest way any function can change.
So here's a final thought. What if your steepest path compass just points nowhere at all?
Hey everyone, and welcome. Today we're going to unravel a really powerful idea in math called constrained optimization, but we're going to do it visually. We'll look at how you can find the absolute best result possible, even when your options are limited, just by using a simple picture to see the geometry behind it all. So, let me ask you something. Imagine you're on a mountain, and your goal is simple: get as high up as you possibly can. But there's a catch. You can't just wander off wherever you want. You have to stay on one specific, marked trail. How would you know when you've hit the absolute peak of your journey? Well, that's the exact puzzle we're solving today. Okay, so first things first. Before we can find the highest point, we need a map of our mountain, one that clearly shows us all the different elevations. What we're looking at here is basically a bird's eye view of our hill. It's a contour map. Each one of these circles connects all the points that are at the exact same altitude. The very center, that's the peak, and as you move out to the bigger circles, you're going downhill. And these lines of constant height, they have a special name. We call them level curves. Think about it this way. If you could walk perfectly along one of these circles, your elevation would never change, not even a little bit. You'd be walking across the face of the mountain, but you wouldn't be going up or down. All right, now for the second piece of our puzzle. We've got the map of the mountain, but remember that catch? We can't go just anywhere. We have to stick to our designated trail. This ellipse you see here is our trail. This is our constraint. The equation is just the math that defines the path, but the important idea is super simple. We can be anywhere on this trail, but we absolutely cannot step off it. This is our entire world of possible options. Okay, now for the fun part. Let's overlay our trail onto the mountain map and start looking for that highest point, the highest we can get while staying on our path. Picture yourself actually walking along that blue elliptical path. As you move, you're constantly stepping over those red contour lines, right? Every single time you cross one of those red lines, your altitude is changing. If you cross onto a smaller inner circle, you're going up. Cross to a bigger outer one, and you're headed down. And this is a really crucial point. If your path is actively crossing a level curve, you can't possibly be at the highest point yet. Why not? Well, because the very act of crossing means that just a little bit further down your path, there's another point on a different level curve, a higher one if you're climbing. The journey isn't over yet. So that leads us to the big question, doesn't it? If crossing a contour line means you're still on your way up or down, where could the highest point possibly be? It has to be at that one perfect moment where you stop going up, just for an instant, right before you start going back down. And this right here, this brings us to the aha moment, the beautiful, simple, visual solution to our whole puzzle. Here it is. The optimal point, the highest you can get, happens at the exact spot where your path doesn't cross a level curve at all. Instead, it just gracefully kisses it. For one brief moment, the direction you're walking is perfectly parallel to a line of constant altitude. This geometric kissing point has a formal name, of course. We call it a point of tangency. It's that one spot where our path and a level curve just touch, sharing the exact same direction at that one specific point. This visual is the key to everything. Now, this whole idea of tangency is way more than just a neat picture. It actually reveals a really deep mathematical truth. And to understand the why behind it, we just need to introduce one more concept: the gradient. Okay, so at any point on our map, there's a direction of steepest climb, right? The fastest way up the hill. A little arrow pointing in that direction is called the gradient, and geometrically, that gradient arrow is always sticking straight out, perpendicular to the level curve at that spot. And guess what? Our constraint path has its own gradient vector too, and it's also perpendicular to the path. Now, let's connect the dots. At our best possible spot, we know the two curves are tangent. That means they share one single common tangent line right there. Now the landscape's gradient vector, it has to be perpendicular to that line. And the path's gradient vector, it also has to be perpendicular to that very same line. So if you have two vectors that are both perpendicular to the exact same line, what does that tell you? They have to be parallel. They're pointing in the same or exactly opposite directions. And that's the big takeaway. That beautiful geometric idea of the two curves just touching is mathematically the exact same thing as finding the point where their gradients become parallel. This visual right here is the foundation for one of the most powerful tools in all of optimization theory, known as the method of Lagrange multipliers. You know, we started with just a simple hike, but this core idea that the best solution happens right where the gradients align is used absolutely everywhere. From figuring out the most efficient shipping routes to managing huge financial portfolios for the highest possible return. So the next time you run into a problem with a bunch of limits or constraints, just remember this picture of two curves gently touching. You'll be visualizing the geometry of the perfect solution. Have you ever looked at a really complex, curvy shape and just thought, how on earth would you even begin to measure that? You know, when our simple formulas for boxes and spheres just don't cut it, we need a much more powerful tool. Well, that tool is multiple integration. And I promise it's not just some scary formula. It's actually the key to measuring the real, messy, beautiful world all around us. I mean, just look at this incredible building. You can't just take its dimensions and plug them into a standard high school geometry formula to find its volume, right? It's way too complex, too organic. So the question is, how does math actually tackle a shape like this? How do we find the volume of something so unique? Well, the answer is, in principle, just beautiful and simple. We don't even try to measure it all at once. Instead, we use what you can think of as a mathematical slicing machine, and that's the core idea we're going to dig into today, breaking down one seemingly impossible problem into an infinite number of totally possible ones. All right, so let's fire up this slicing machine. Its most basic setting, its bread and butter, is the double integral. This is our go-to tool for taking a complicated 3D shape and figuring out its volume with absolute precision. Okay, so imagine this wavy, curved surface just floating in space. Our mission is to find the exact volume of the space that's tucked between this surface and the flat XY plane right underneath it. That volume, no matter how weirdly shaped it is exactly what a double integral is built to calculate. So how does this slicing machine actually pull it off? It uses this really clever inside-out method. First up, the inner integral. Think of it like a laser that scans and calculates the area of one single paper-thin slice of our shape. Then the outer integral takes that 2D area and just sweeps it across the entire base, adding up the tiny volume of every single one of those slices to give us the grand total. It's a brilliant strategy, really. You turn one hard 3D problem into a whole bunch of much easier 2D problems. Now, here's the cool part. Our slicing machine comes with a kind of superpower, a feature that gives us incredible flexibility and honestly just makes our lives way easier. It's a cornerstone of this whole process, and it's called Fubini's theorem. Think about it like slicing a loaf of bread, right? You can make your cuts vertically, or you could turn the loaf on its side and make horizontal cuts. Well, Fubini's theorem tells us we have the exact same choice with our integrals. We can choose to slice parallel to the y-axis first, or we can slice parallel to the x-axis first. The choice is ours. And this is the awesome guarantee Fubini's theorem gives us. It says that as long as our function is continuous, no crazy jumps or holes in the surface, it does not matter which way you slice it. The final volume you calculate will be exactly the same. So what does that mean for us? It means we can always choose the order of integration that makes the math the simplest. It's a game changer. So our slicing machine is really powerful, but its default setting uses a square rectangular grid. And as you can probably guess, trying to measure something round with square tools, well, it can get pretty messy and inefficient fast. I mean, just look at the difference here. Trying to describe a beautifully smooth circular curve using a clunky, blocky, rectangular grid, it really is like trying to force a square peg into a round hole. It just feels wrong. There has to be a better way, right? And of course, there is. Instead of learning a whole new set of rules, we just change the attachments on our machine. We switch to a coordinate system that actually matches the natural shape of our object. For flat circles and spirals, polar coordinates are perfect. For things like pipes or cans, cylindrical coordinates are tailor-made for the job. And for spheres or parts of spheres, spherical coordinates are the ultimate tool. Okay, but there's a catch. When we switch from our standard square grid to these new curvy attachments, our machine needs a quick recalibration, just to make sure its measurements are still spot on. And this brings us to those kind of mysterious extra factors that suddenly pop up in our integrals. Let's just address the elephant in the room, because this is a question that trips up pretty much everyone when they first learn this. Why do we suddenly have to multiply by an extra r when we switch to polar coordinates? Or that even more complicated-looking rho squared, sine phi, and spherical? Are these just some random rules we're supposed to memorize? No, absolutely not. They are essential calibration factors. Think about it. In polar coordinates, your little wedge-shaped slices get wider and wider the farther they get from the center. That extra factor r is the exact correction we need to account for that change in area. And it's the same idea in spherical coordinates. That rho squared sine phi thing perfectly accounts for the really complex way that spherical shells stretch and curve. It's just the machine's way of making sure every single piece, no matter how curvy, gets measured perfectly. So far, we've pretty much only talked about calculating volume. But honestly, that's just the warm-up act. The real power of our slicing machine, of multiple integration, is how unbelievably versatile it is across all of science and engineering. Using the exact same ideas of slicing things up and adding them back together, these integrals can calculate the mass of an object where the density isn't even constant. They can find its center of mass, its perfect balance point. In statistics, they're used to figure out the probability of multiple things happening together. And in physics and engineering, they tell you an object's moment of inertia, which is basically its resistance to being spun around. The applications are literally everywhere. It all comes down to this one single powerful idea. This is really the heart of all integral calculus. If you can understand and describe the tiny, infinitesimal pieces of a system, then you can add them all up to perfectly understand and measure the whole darn thing. So, the next time you see a complex curved shape, whether it's a mountain, a piece of art, maybe even a cloud, you now know the secret. It can be understood, it can be measured. You just have to have the right mindset and approach it one slice at a time. So my question for you is, what complex shape in your world are you going to measure first?
All right, let's tackle a classic calculus mystery. Ever wonder where that extra r in integration comes from?
I mean, a circle seems simple, right? But with regular xy coordinates, the math gets ugly fast.
See, on a standard grid, we use tiny squares. It's like trying to build a perfect circle with Legos.
So we switch to polar coordinates to make it fit better, and boom, this mysterious r just shows up.
So what are polar coordinates? It's just a different way to map things, using distance and angle.
And here's the big deal. The grids look totally different. Polar grids aren't uniform. They stretch out.
Okay, let's zoom in on just one of these little wedges. The answer to our r mystery is right here.
The idea is simple. Find its height and its width. But as you can see, they're not exactly straight.
The height part is easy. It's just a tiny step away from the center, which we call dr.
But that width, well, that's a curve, an arc. And for that, we need a little bit of geometry.
And this is the secret. The length of that arc isn't just the angle, it's r times the angle.
That r is there because the farther you are from the center, the wider that little slice gets.
So you multiply them, height dr times width r d theta. And there it is. That's our missing r.
And get this same idea isn't just for 2D. It extends right into 3 dimensions.
So for cylindrical and spherical coordinates, you get new scaling factors for the exact same reason. So why do we even care? Because this little trick turns ridiculously hard problems into simple ones.
Trying to find the volume of a cylinder in Cartesian is a nightmare. In cylindrical, it's a piece of cake.
This is the kind of math that lets us build everything from jet engines to amazing architecture.
So that extra r isn't just a rule, it's hidden geometry. Makes you wonder what else we're missing, right?
Welcome to the Explainer. We're surrounded by stuff we can't see, forces that shape everything from the orbit of planets to the flow of a river. Today, we're going to learn the language that lets us see it. That language? It's vector calculus.
Think about it.
Right now, the invisible force of gravity is holding the Earth in its orbit around the Sun. On a windy day, you can feel the air pushing you around. These are invisible forces, right? We can't see them, but with vector calculus, we can actually draw a map of them.
So, how in the world do we describe these invisible landscapes? How do we measure them or even predict what they're going to do next? Well, that's exactly what vector calculus is for.
All right, so here's our game plan for this explainer. We're going to start with the basics, vector fields. Then we'll see what happens when you move through them. That's work along a path. We'll zoom in to look at divergence and curl, what I like to call sources, sinks, and spin. Then we get to the really cool part, the great shortcuts. And finally, we'll tie it all together and see how it all connects. Let's get into it.
Okay, first up, welcome to vector fields. This is our map of forces. It's our way of visualizing all those unseen pushes and pulls.
So what is a vector field? Imagine you could put a tiny arrow at every single point in space. Seriously, every single point. Each arrow tells you two things: how strong a force is at that spot, that's the arrow's length, and which way it's pointing. It's like a complete map of an invisible force.
And this isn't just some abstract math concept. I mean, these fields are everywhere. We're talking about the force of gravity, the wind patterns you see on a weather map, that's a classic vector field, the flow of a river, even invisible electric and magnetic fields. It's the language we use to describe all this stuff.
Okay, so we've got our map. Now let's start moving through it. What happens when you try to walk through this field of forces? How do we measure the total effect it has on you?
For this, we need a tool called a line integral. It sounds complicated, but the idea is actually pretty simple. If you're walking along a path through this field, the line integral basically adds up all the little pushes and pulls you feel from the field along your entire journey. It tells you the total effect the field had on you.
And this picture of the kid with the wagon? It's perfect. The amount of work you're doing isn't just about how hard you pull. The angle is everything. If you're pulling with the path, great. All your effort helps. But if you're pulling against it or at an angle, only some of your effort is actually doing the work. A line integral is just a math that figures all that out, summing up that effective push or pull over the whole trip, no matter how curvy the path is.
Okay, so far we've been looking at the big picture, the total effect over a whole path. But what if we zoom way in, down to a single point? We can ask a different question. Is the field expanding out from this point or contracting in?
This brings us to divergence. All divergence tells you is this: at one specific point, is the field flowing out of it or flowing into it? Is it a source of stuff or a sink where stuff disappears? And the idea is super intuitive. See here, positive divergence is a source. Think of a sprinkler head just spraying water out in all directions. The field is expanding. Negative divergence is a sink, like water going down a drain. The field is contracting, flowing inward. And hey, if the divergence is zero, it's just flowing through, like a steady river. Nothing created, nothing destroyed right at that point.
Right, so a field can flow in or out, but it can also swirl, and that's our next big idea, curl. Even in a river that looks like it's flowing straight, you can have these little whirlpools, right? That's what we're talking about.
So curl is all about measuring the rotation of a field right at a single point. It's not about the whole field turning a corner, it's about the microscopic, local spin, the little eddies in the flow.
This little paddle wheel is the perfect way to think about it. Imagine you could drop a microscopic one right into the field. If the forces around it make it start to spin on the spot, then you've got curl. If it just gets carried along without rotating at all, then hey, the curl is zero right there.
Okay, now for the really cool part, the magic trick, you could say. We've been looking at these local things, like curl at a single point. Now we're going to see how they connect to the big picture. Because let's be honest, calculating those line integrals can be a real pain. But guess what? There are shortcuts.
And our first big shortcut is called Green's theorem. Look, you can figure out the total flow around a closed loop the hard way, adding up every tiny little segment of the boundary. Or you can use the shortcut. Green's theorem says that whole calculation is exactly equal to just adding up all the tiny little spins, the curl, on the entire surface inside the loop. How amazing is that? The boundary behavior is totally defined by the stuff happening on the inside.
And this idea, this shortcut, it's not just a one-off trick. It's part of a much bigger, more beautiful pattern that really ties all of vector calculus together. It's a fundamental principle of how nature seems to work.
Take the divergence theorem. It's another one of these incredible shortcuts.
It says the total amount of stuff flowing out of a 3D shape, like a box, is exactly equal to the sum of all the little sources and sinks on the inside. So, you want to know the total flow out? You don't have to painstakingly measure the flow across all 6 faces of the box. Nope, just add up the strength of all the sprinklers and drains you've got on the inside. Same answer. Mind-blowing.
And then there's Stokes' theorem, which is basically Green's theorem but in 3D. It says that the total flow around the edge of any surface is equal to the total amount of spin, or curl, happening on the surface itself. Think of a butterfly net in the wind. The total circulation of air around the rim of the net is determined by all the little swirls happening across the surface of the net. The edge is a summary of the inside.
So this is it. This is the big, unifying idea. All these major theorems are telling us the same profound story. What happens on the outside, on a boundary or an edge, is completely determined by the collective behavior on the inside, whether that's divergence or curl. It's this beautiful relationship between the inside and the outside of everything.
So we've used this language to map these incredible fields of force and flow, things we can't even see. It has given us the tools to understand gravity, electromagnetism. I mean, it literally reveals the hidden structure of our universe. So the real question is, what other invisible landscapes will we map next?
Okay, let's dive into the world of vector fields and what makes some of them conservative. We'll start with a simple question to get us thinking. Does the path you take really matter? Imagine 3 hikers. They start and end at the same spots, but they all take different routes. Our first hiker, super ambitious. They take a steep, direct path straight up the mountain. The second hiker prefers a winding route. It covers more ground, but it's a much gentler climb. And hiker 3 has a change of heart, starting steep before switching to the easier path. So, if we only think about the force of gravity, on which hiker did it do the most work? The answer is kind of surprising. The work done by gravity was exactly the same for all 3. This is a property we call path independence. The journey doesn't matter, only the destination. And this perfectly illustrates why fields like gravity are called conservative. They actually conserve energy. You see, any field that's path independent is, by definition, a conservative vector field. It's a direct link. But checking infinite paths is impossible. We obviously need a practical test, like a mathematical shortcut. And that shortcut is a measurement called curl, which tells us about the field's rotation. Think of curl as the local spin at any point in the field. Some fields spin, others don't. Here's a great way to picture this. Imagine dropping a tiny little paddle wheel into the field. If that paddle wheel starts to spin, the field has curl. If it doesn't move, the curl is 0. Now, here's what's so cool about this. Conservative fields always, and I mean always, have 0 curl. Let's see how this all connects. These 3 ideas are fundamentally linked together. It's a beautiful thing. So the big takeaway is that this gives scientists and engineers an incredibly powerful tool. Which leaves us with one final thought. When can a simple shortcut reveal something truly profound?
All right, so if you've got a handle on single variable calculus, finding slopes and areas, then you are ready for a pretty huge step up. We're about to go from the flat world of lines and curves into the rich, 3-dimensional world of landscapes. Let's dive right in.
To get our bearings, let's just start with a big question. How can we possibly use calculus to describe a mountain? I mean, it's not some simple curve, right? It's got height, it's got width and depth, and the slope changes completely depending on which direction you're facing. Well, this is exactly the kind of problem multivariable calculus was designed to solve.
So what's the real game changer here? Well, on the left, you see a familiar parabola where y only depends on x. Simple enough. But on the right, we've got a full-on surface. Here, the height, which we're calling z, depends on 2 things, x and y. That one little change, just adding one more variable, is what takes us from a flat curve to this amazing complex landscape.
Okay, so we're officially leaving the flatland behind. And you know what? The rules are about to change, because this new world we're entering is so much richer and way more complex. Think about it like this. With a function of just x, you can really only move forward or backward along a line. But with a function of x and y, you've got total freedom. You can move in any direction you want across a whole plane. And that freedom, well, that's what makes everything so much more interesting.
So how on earth do we visualize these 3D shapes on a 2D screen? Well, we use something called a contour map, which is basically a topographical map, like you'd use for hiking. Each of these oval lines represents a set of points x, y that all have the exact same height. And you can see, where the lines are bunched up together, the surface is really steep. Where they're spread far apart, it's pretty flat. This is going to be our map for this new terrain.
Okay, so we've got our map, but a map's no good without a compass to navigate it, right? Our first and most fundamental tool for that is the partial derivative. And you'll probably notice that new notation there, that kind of curly D symbol. We call that del, and it's a signal for a partial derivative. It's basically a heads up that our function has multiple inputs, but for right now, we're just focusing on how it changes with respect to one of them, while we hold all the others steady.
And here's the secret that makes this whole thing surprisingly easy. When you want to find the partial derivative with respect to x, you just treat y like it's a constant. Seriously, just pretend it's a number, like 5. Freeze its value, and then all the rules you already know about regular derivatives just apply perfectly.
Let's actually break that down. First, you pick a direction, let's say the x direction. Then, you look at your function, and you just mentally lock down the y variable. Just think of it as a fixed number. And finally, you just take the derivative with respect to x, like you always have. It's this really clever way of simplifying a complicated problem by just looking at one slice of it at a time.
Let's go back to our mountain. Imagine you're standing right there on the surface. The partial derivative with respect to x, that's the steepness you'd feel if you only walked east or west. The partial with respect to y, that's the steepness if you walked purely north or south. It's your slope, but in two very specific directions.
Now, those two directions are super useful, but let's be honest, we have infinite directions we could choose from. To handle that, we're going to need a much more powerful tool, and that tool is the gradient.
This is the crucial question, isn't it? Knowing the slope if you walk east and the slope if you walk north is great, but what if you want to walk northeast? Or, in any other random direction? Partial derivatives by themselves, they just don't tell us. We need some way to combine all that information.
And that is exactly what the gradient does. It's a vector, and we use this upside-down triangle symbol for it, called nabla. Its components are simply the partial derivatives we just learned how to find. But here's the amazing part, the superpower of the gradient. At any point on your surface, this vector points directly uphill. It points in the direction of the steepest possible climb.
So let's go back to our contour map. If you want to climb a mountain as fast as possible, you don't walk along a contour line, right? That would keep you at the same height. No, you walk straight across them, and that's exactly what this image shows. The gradient vector is always perpendicular, at a right angle, to those level curves. It's the mathematical way of saying, point me straight up the hill.
So now that we have our map and we have our compass that always points uphill, we can finally tackle the main event, the ultimate goal of optimization, finding the highest peaks and the lowest valleys on our entire landscape.
What's the one thing that the very top of a mountain peak and the very bottom of a valley have in common? Well, they're momentarily flat. If you're standing right at the summit, the ground is basically level in every direction, right before it starts to slope down again. So let's connect the dots. If the gradient points in the direction of steepest descent, what happens when there is no direction of ascent? Well, the surface has to be flat, and mathematically that just means the gradient vector has to be the zero vector. Both of its components, both partial derivatives, have to be zero at the exact same time.
Let's actually put this side by side with what you already know from Calc 1. Remember finding critical points? You just set the first derivative to 0. Here, we do the same thing. We set the gradient to 0. Back in 1D, you used the second derivative test to figure out if it was a max or a min. In 2D, guess what? We also have a second derivative test. Now, it's a little more involved, sure. It uses this value d that combines all the second-order partials, but the core idea is exactly the same. Here, look at this concrete example. For this sort of bowl-shaped surface, the math tells us that the gradient is only 0 at one single spot, the point -1, 2. That's our critical point. It's the very bottom of the bowl. And then we can use that second derivative test to confirm, yep, that's a local minimum. Our tools work perfectly.
So let's just take a breath and recap the journey we just took. We saw how adding just one little variable takes calculus from flat curves to these amazing 3D surfaces. We learned that partial derivatives are just slopes, but in very specific axis-aligned directions. We saw how the gradient vector bundles all that information up to point us straight uphill. And finally, we use that knowledge to hunt for peaks and valleys by looking for places where that gradient is 0.
We've gotten pretty good at analyzing a static, frozen landscape.
But here's a final thought to leave you with. What if the landscape itself was in motion? What if instead of a mountain, we were trying to analyze the velocity of water at every single point in a flowing river? What new kinds of calculus would we even need for something like that? Well, that's a great question. For the next step in our journey, vector fields.